we were talking about like the 3 different rules for series circuits. Okay, and I already said that the first rule was about the voltage on a series circuit. Okay, so let's see if this is going to work now and it doesn't go back into darkness. So I said that RT was equal to the sum of all the resistance that we have around the closed loop, that the total voltage is equal to the sum of all the voltages as per Kirchhoff's law. And something which is extremely important going forward into combination circuits, we have to be able to remember that the total current around a closed loop will always be equal on each individual component. Okay, so those are the 3 rules for series circuits. Now, if we go back and we look at the questions here, and we look at the questions that say, okay, so what's going to be our voltage? Okay, let's get back into. So if we go back into this handout, where we have like the different questions about what's going to happen whenever the switch open. So from the simulation itself, we were able to see that when the switch is open, the different voltages that we are going to obtain, well, with the switch open, the voltage between A and B is going to be equal to 100 volts. I was telling you before everything got interrupted because my computer froze, is that I wanted you to be aware of the fact that the highest voltage drop that we experienced so far was on the 60 ohm resistor, because that resistor requires the highest push in order to be able to push the current, which is the electron flow through that special and specific component. Okay, so that's why that your voltage is going to be divided according to the value of your resistor. By all means, of course, if we open the switch between the test point A and B, if you were going to measure an open switch with an ohm meter, okay, what do you think the ohm meter will read? Can you hear me?
Yeah, we hear you. What are you asking?
So the question was, okay, so if we use an ohm meter and we measure the ohms, the amount of ohms that we have across an open switch, how many ohms?
100?
Okay, like if we measure the ohms, the ohmic value of an open switch, how many ohms do you think we'll get?
OL.
Perfect. OL, which means that it's going to be over the limit of the ohm meter to be able to measure that value. Probably with a mega, we would be able to get something, but chances are, because that we won't get anything at all. Okay, it's just going to be reading OL, even with a mega that can read giga ohms. So that means that the amount of resistance that we have through an open switch is equal to infinity. Okay, so that being said, I want you to keep in mind that when we were simulating the circuit, we were experiencing the highest voltage drop on this resistor. Why? Because that one have the highest resistance value. So you can imagine, like if I were going to plug in a device that have an infinite amount of resistance, that device would be taking all the voltage, I mean, that we are going to apply to the circuit. So it would be taking the full voltage drop. So that's why that when we open the switch, we are going to have full voltage drop across the terminals of that switch. And because the switch is open, like if these were light bulbs, and we have a switch open, of course, all the light bulbs will be off. And that's because all of things will have 0 volts. Okay, so source voltage will never be interrupted. Source voltage will always remain the same, regardless of what you are doing to the circuit. So GH, it was 100 volts. AB, which is the terminals through my open switch, is going to be 100 volts as well with the open switch. And then everything else is going to be equal to 0 volts. Any questions about that? Are we okay?
Yeah, I think we're good.
Yeah.
Yep.
Okay, so let's get moving. Now, when we happen to close the switch, okay, let's close the switch now. If, I'm just going to give you this as background information, if we have a closed switch and we measure the ohmic value of a closed switch, how many ohms do you think that we are going to read through a closed switch?
0.
0 ohms. Okay, perfect. So if we have 0 ohms between points A and B when the switch is closed, how much voltage do we require in order to be able to push the electrons through those points?
0.
0 volts. Perfect. If we don't have any resistance, then we don't require pretty much like any voltage to be able to push the electron through it. Okay, so we don't experience any voltage drop. So when the switch closes, okay, as I said, source still is going to be the same, regardless of the condition of the switch and regardless of the condition of your circuit. However, between point A and B, once the switch is closed, we are going to have 0 volts. And then the different voltages are going to happen or are going to be a drop depending on the value of each individual resistor. Okay, so in this instance, the value between C and E, in that case, we are going to apply Kirchhoff voltage law. And we are going to say that, okay, between C, which is this test point here, and E, we have 2 resistors. So if I connect my voltmeter between these 2 points, we are going to get 90 volts. If we connect the voltmeter between points C and F, okay, so now I'm going to be using my DF point here. So of course, the voltages on each individual resistor is going to be adding up. So in this case, we are going to have 60 plus 30 plus 10, that's going to be equal to 100 volts. Now, once more, okay, and this is very important, I want you please to remember that always around a closed loop, the sum of all the voltages will be equal to the source voltage, okay? Source voltage doesn't necessarily has to be the battery, but it can be the component which is connected in parallel with that closed loop. And just to end with this part of the simulation, so the voltage drop that we are going to have between D and F, between those 2 points, is going to be 30 volts. And between D and E, D and F, I'm a little bit too quick. D and F is going to be 40 volts. And D and E is going to be 30 volts. And all that I was looking for, like in adding all these voltages, is that you keep using over and over and over that reasoning that E1 plus E2 plus E3, giving you like whatever voltage you are measuring with the voltmeter. Any questions about that so far?
No, I think we're good.
No, I think we're good.
We are good. Okay, perfect. So let's keep moving. So what I'm going to do now and what we're going to do next is that, okay, so what's going to happen if, okay, so what's going to happen if the resistor R1 were to burn out? So first, we are going to see it. We are just going to discuss it very briefly, and then I'm going to show you the simulation on what's going to happen with it. Okay, so in this instance, if that resistor R1 were going to burn out, which is this one that we have in here, as I said before, source voltage will never change. Okay, so I want you to keep something in mind. When that resistor burns out here, and if I measure with an ohm meter the value of the resistance across an open resistor, I'm going to get pretty much infinite resistance. That being said, then that would mean that I would be getting through point C and D 100 volts, all the full voltage drop of your source voltage, okay? And then I would be getting like 0 volts even in all the other components. And in that case, because that resistor is open, it doesn't really matter if I open or if I close my switch, still I will be reading 100 volts across the open component, the open device. And that's a troubleshooting technique, actually, okay, guys? Like if you ever go to a wall switch and you measure and you don't get like full voltage, you don't get your 120 volts between the neutral and one of the terminals of your wall switch, immediately you know that the breaker has to be off or that the wire was cut off somewhere along the line, because you should always have 120 volts between the neutral and your switch, okay? Any questions about that?
I think I'm okay.
Are we okay?
Yeah, I think we're good on that.
Okay, perfect. So the last portion, just to show you, like just that you know, like in the simulation, I didn't find anything to open the circuit. But in the simulation, what I did is that I simulated that we have, that the resistor just developed a very, very high resistance. So what you are going to do is that, I mean, when you check the simulation, you are just going to slide, you are just gonna play with the slider here, and you are gonna crank it up to 10 mega ohms. And by having the 10 mega ohms, you can see that by all means, we get full voltage. And it doesn't really matter what I do to that switch. Well, actually, like, this is not open, it's just 10 mega ohms, okay? So if this was completely open, instead of being 10 mega ohms, then this would remain at 0 anyways. So now let's jump into parallel circuits. Do you have any questions about series circuits or about any of the rules or about any of the problems that you have solved so far?
I was curious about circuit 9 in the series handout that had the flow coming to and from ground.
Okay, so let me take a look at that. So that is in which handout? The number 2?
I believe it's the series circuit handout.
Okay.
Yeah, the second one.
The second one, right?
Yeah, the one that has all the circuits and you're looking for like the voltages and power in them.
So did you check the, okay, so the only thing you gotta keep in mind here,
Can you show us your screen so we can see what you're talking about?
oh, sorry. I thought you were able to see it. So just give me 1 second here. Okay, so it's that one. So, okay, so something that you gotta keep in mind.
No, the next one, circuit 9.
Circuit 9, right?
Yeah.
That one, perfect. So remember what I was talking about, like additive and subtractive polarity? So in this instance, you can see that here we have a ground reference. And from the ground reference point of view, okay, you can see that the positive terminal, this positive terminal around the closed loop is connected to the negative terminal. So in this instance, we have additive polarity. So you have your 9 plus 6, which is going to be equal to 15 volts applied. This is the same thing that I was doing when I did the simulation that I posted online. So what was the question about that part that you were confused?
I just was confused because it didn't look like a closed circuit. So because there's ground on each side, we're assuming the current's just going to flow through ground.
Perfect. Like in large circuits, this is just for reference. Large circuits, usually like in electronics, you're not going to be able to see, I mean, you are going to see the symbol all the time, which is the ground symbol, because you just cannot draw everything back to the ground with a line. So instead of having like on large schematic diagrams, you are just going to have a ground, meaning that everything is going to be connected back to the ground. When you study like level 1 electronics, like project number 5 and 6, on those projects, you will see that you are going to see the symbol on those schematic diagrams. And it just means that that component or that portion of your device is connected back to a common point, which is your chassis ground in this case.
Okay, yeah, and then you said chassis ground there, and I was also reading there's stuff like earth ground. What's like the difference and what's the importance?
Perfect. That's a great question. Thanks for asking that. Okay, so when you like in residential, okay, so let's just make a comparison. Okay, like if you have a panel, 100 amp panel in a residential household, you have to use what is called in situ grounding. And the in situ grounding, or you can use a grounding rod or a grounding plate, 2 grounding rods or a grounding plate, but in situ grounding is what is mostly used in the city. And it just means that from your panel, here you have your water pipe, your water meter. So you are going to be sending a wire, a number 6 conductor, straight into that pipe. Okay, so when you send it to the water pipe, which is a metal pipe, then this wire here is called a grounding conductor, a grounding wire. Okay, now anything else which is going to be connected to the grounding bar is actually not grounding, it's just bonding. Okay, so any other receptacle or switches which is connected through the green wire to here is just bonding. So this is called here bonding. Okay, so now the difference is a grounding conductor provides a path to the ground, a clear, a low impedance path to the ground, while a bonding conductor, it just makes sure that all non-conducting metal parts of any electrical system have the same ground potential. Okay, so that is your earth. So this one here is your earth ground. Now, on the flip side, when we are talking about our chassis crown, think about a car, okay? Like in a car, you have a battery. And in the battery in your car, you have your positive and negative. And have you ever jumped a car? Have any of you ever to use couple cables to jump your car?
Yeah.
Yep.
So how do you connect it? How do you make the connections from the other car to the car that you want to jump?
What do you mean, like negative to negative, positive to positive?
Yes, but the way you do it is that you take the red wire, okay, and you connect it to the donor. And then you take the black wire and you connect it to the chassis, to the actual chassis of the car. And then it goes from this negative to the chassis of the car. Okay, you never connect it to the actual negative terminal. So why? Because this negative terminal is connected to all the metal components of your car, and that is called chassis crown. It is, in other words, it's just bonding, but it doesn't create a path to the crown. That's the difference between the two. Chassis crown, it is a common point of connection, while grounding, it is a connection to the actual crown. Does it make sense?
Yeah, that makes more sense. Thank you.
You're welcome. So, okay, so let's keep moving, guys. So let's jump into parallel circuits. In the case of parallel circuits, I also has created another simulation for that. So under week 3, and on the parallel circuit, I mean, you had a bunch of stuff to do. And that's why that you have the answer key available for each individual handout. And that way you can go back and forth and see if you are, understanding the information, or if, some questions comes up. Now, from here, there's an important problem that I posted, which is called like a parallel circuit quiz. And this is when you know that you really understand. I mean, when you can solve this problem, this is when you can tell that you understand the 3 rules about parallel circuits. The 3 rules dictate. Okay, so let's go through the 3 rules for parallel circuits first. Okay, the first rule says that the total voltage on a parallel circuit will always be equal in all the branches that are connected on that parallel circuit. Okay, so if we have a power source, we had a battery, we have here a field resistor. Okay, that's just a simple circuit. But as soon as we create a node right there, and as soon as we branch off and connect another component to that node, I'm going to call this node connection point A, and I'm going to call this node connection point B. As soon as I connect another component to that node, this other resistor is going to get the same potential difference, the same voltage that we are getting on R1. And that is not a secret. That's why that in residential, commercial, doesn't matter, industrial, everything, pretty much like all the outlets, lights, everything is connected in parallel. All the breakers, everything is connected in parallel, okay? Of course, the like all the breakers, all the branch circuits, all the breaker protecting branch circuits are going to be connected in series because you want them to be able to interrupt the current in case of an overcurrent situation. But in the case of the actual loads, all the loads are going to be connected in parallel. Why? Because of this characteristic that voltage remains the same in all the different branches. Okay, so the other rule that we have is that the actual current is going to add up. And then we get to something which is called Kirchhoff's current law. And Kirchhoff's current law dictates that all the current that enter and leave a node the algebraic sum of all the current that enters and leaves a node will always be equal to 0. Meaning that if I were going to have, let's say, 3 amps getting into that node, the current is going to split. Like, let's say that in this case, we have 2 resistors that are of equal value. So if that was the case, I would be getting 1.5 amps on both resistors. Any questions about that?
No.
Okay, so we're good. And now the other, okay, so the other thing that you need to know are the formulas that we use in order to find the total resistance in a parallel circuit. And in this instance, we have 3 different formulas. The first formula will be resistors of equal value. The total resistance of resistors of equal value, okay, this formula only applies when we have resistors of equal value, is going to be equal to the value of any of the resistors. Let's say that here we have 60 ohms, and here also on R2 we have 60 ohms as well. So in this instance, we are going to take the value of one resistor and we are going to divide it by the number of resistors that we have connected in parallel. So in this case, we would have the 60 ohms divided by 2, because we have 2 resistors, is equal to a total of 30 ohms. Are you surprised that when we are adding new branches, that the total reciprocal resistance of the circuit, it actually goes down? And that is completely consistent with Ohm's law. Are you surprised about that, or anybody wants to comment about it? We're good?
Yep.
Yeah.
Okay, so just keep in mind, guys, that when voltage goes up, current goes up. When voltage goes down, current goes down. Now, when resistance goes up, current goes down. And when resistance goes down, current goes up. And just keep that in mind. So in this instance, like if I only had, okay, let's say if I had a switch here and I open the switch, I will only have 1.5 amps through it, okay? As soon as I close that switch, because I am opening a new branch, I am opening like a new path for the flow of electrons. Because I just opened a new path for the flow of current, the total current in my circuit will increase. I mean, and in order to be consistent with Ohm's law, if my current was increasing and my voltage has remained the same, because we haven't changed that voltage, that means that the total resistance called the circuit has to be dropping, has to be going down, because that's the only way by which that we are going to be able to increase current, the total current in a circuit, without increasing voltage, because they are inversely proportional. Okay, so let's get moving. So the other rule If you don't have any questions about that, the other rule, in order to find the total resistance in a parallel circuit, is called product over sum. And that dictates that if I have R1 and I multiply R1 times R2, that's the product over the sum plus R1 plus R2, that would be equal, let's see if that's going to work. Let's see if we are going to be getting 30 as well, okay? That would be equal to 60 times 60 divided by 120. Okay, so in that case, with all confidence, like if we do 60 times 60, 1 second here, we're going to be getting 3600 divided by 120. That's going to be equal, of course, to 30 ohms. So you can see that both formulas are consistent. Remember, this is when all of them are equal, and this is when we have two resistors only. Okay, now you may wonder, okay, so what happens when I have more than two resistors? If you happen to have, let's say, 3 resistors and more, then you are going to use what is called the reciprocal formula. In that case, okay, let's say I'm going to give you like 3 resistors. And let's say this one is 60, this one is 30, and this one is 20. Okay, so in this case, we are going to use the reciprocal, which is that the inverse, that is called the inverse of the sum of all the resistors is going to be equal to RT, to the total resistance. So there's like in your calculator, you have a key. So I'm going to show you on the screen that allows you to calculate those values. Give me just 1 second here, and I'll show you. So you can see my calculator now, hopefully. Can you see it?
Yep.
Okay, perfect. So if you notice this key here, okay, like this key, that key is the key that is used in order to find the reciprocal value in parallel circuits. Also, it could be like 1 divided by x, or the symbol could be x to the minus 1. Okay, it just depends on how you have it on your calculator. Now, the values that I gave you before, they were based on, we said that we had 60 ohms. And then we click this key, plus 30 ohms. And we click this key again, plus 20 ohms. And we click that key again, and that's going to give us 0.05. And then we have to click one last time that key again in order to get our resultant, which in this case would be 20 ohms. Any questions about that? Or we are good?
No, sir.
Pardon me?
No, we're good.
We're good? Okay, perfect. So, okay. So when it comes to this circuit here, okay, so I don't think we are going to have enough time, like unless you have, do you have more time today so we can finish this? or you have to go to another class?
We have a few more minutes.
I'm
I
good.
got stuff to do.
Pardon me?
Got stuff to do.
Okay. So what I'm going to do, like those of you that can stay. Those of you that cannot stay, that's fine. You can log out. What I'm going to do, I'm just going to explain this circuit, and I'm going to show you the simulation as well. And then I'm going to post it online. And those of you that didn't have a chance to stay will be able to at least go to this part of the class and just look at it, okay? Fair enough? So let's get moving. Now, let me do something. Gotta stop this chair. From this circuit, we have the following. From this circuit, we have that we have a power source, which is 130 volts. We have to keep in mind the three different rules that we were talking about, okay? So I'm just gonna write them here so we can refer to them in case we need to. And I'm just gonna use two resistors for now, okay? Okay, so I wrote the three different rules on the side of the screen. Hope you can see it well. So let's get moving here. So we have an applied voltage, which is equal to 130 volts. And what I'm asking you in this case is that we use this rule here at the bottom. We are going to be using this rule in order to determine what's the amount of current that we have on each individual ammeter, okay? As I said, I just posted a link with a simulation for this so you can enhance your learning with it. So let's begin. In this case, like if I want to determine like the value for all these ammeters, all I have to do, number one, I have to know what is my total resistance. So please go ahead. I'll just give you like a minute and go ahead and calculate what is the total resistance, okay, for this circuit. And please just comment.
Is it 11.3 ohms?
Yeah, that's what I got.
That's what I got as well.
Greg? Greg, are you there?
I think I heard him walk
Yes,
away.
I'm here. Sorry, my mic just muted for a moment. Okay, so you said how many ohms we have in total?
11.3.
11.3 ohms. Perfect. So that means that if we use Ohm's law and we do 130 volts divided by 11.3 ohms, we would be able to get our total current, right? Which in this case is how much?
11.55.
11.55 amps. Perfect. So something that we got to keep in mind, it doesn't really matter if we are going to use the electron flow theory or if we were going to use the conventional flow theory. In either case, we still have the same 11.55 amps, okay? So that means that if we have 11.55 amps, and I just like to use the clockwise fashion, those are nodes. If I have 11.55, that's going to be splitting between 4 different branches. And then everything is going to recombine at the end and flow through A1 in order to return, in order for the current to return to this terminal, okay? So yes, indeed, we have 11.55 amps for A1. How much do we have for A2? Then we got to remember that in order to determine A2, this rule for having the same voltage across all the branches in a parallel circuit is always equal. And that makes life so easy because we can very quickly determine what's the current on each individual branch. So we are going to have 130 divided by 25. That's going to be equal for A2 to 5.2 amps, right? Then A3, same thing, 130 divided by 52. That's going to be equal to 2.5. Now, when it comes to A4, we got to be very careful here. A4 is the resultant of the current that is flowing through R3 and the current that is flowing through R4, okay? So both currents are going to be joining right here on this node, and then they are going to flow together through that ammeter R4. So something that you can do if you like, and I'm just going to do it that. I'm just going to do that for simplicity's sake. I'm going to say 130 divided by 104. And that's going to give me 1.25 amps for that load. And they say 130 divided by 50, and that's going to give me 2.6 amps. Now that I have 1.25 plus 2.6, I can apply this rule. And then I'm going to get for R4, 3.85 amps. For the last one, which is A5, it doesn't really matter if I have A5 on the top or if I were going to connect this inline ammeter at the bottom. It doesn't matter where I place it along this line. Still, it will always measure my 2.6 amps. So far, so good. Any questions?
Yep.
So we are good. Okay, perfect. So now it becomes very interesting once we open the table. Okay, so let's just keep, please, these values in mind. So what I'm going to do, okay, I'm going to say that A1 was 11.55. I'm going to write them beside here because I don't want to lose these values. Perfect. So that way we don't lose any of the values. So now let's scroll. Let's get rid of all this so we can scroll down. Okay, so what we are going to do is that now we are going to use all these symbols, up arrow, down arrow, a check mark, and a zero in order to indicate what is the condition of all the different ammeters depending on, on the given circumstance in this instance. So let's begin. If switch 1 and 2 closed, okay, so let me see if I can get this back slightly. Here, okay. Can you still see it on the screen? I can see it very well on mine. Okay, so if switch 1 and 2 are closed, then we already know what's going to be the value for everything, right? So we already know all these values. I'm going to write them down once more. Okay, perfect. So let's keep going. Now, what's going to happen when switch 1 opens up? What do you? I'm just going to let you think about it. What do you think is going to happen when that switch opens?
No current will flow through resistor 1.
Perfect. So what I'm going to do, I'm just going to show you very quickly the same circuit simulated. Okay. So if we open, that was switch 1, right? That opens up. Look at what happens right away. As soon as switch 1 opens up, we are going to have 0 amps because, of course, we are opening that branch. But also we can see that the total current on the ammeter drop. It used to be 11.55, so it drops to 6.35. However, we can see that these other ammeters remain unchanged. Okay, so nothing happens at all to them. Why? Because these other branches don't feel the effect on what's happening on this individual branch. So each branch is independent and it's going to be taking its own individual current. Okay, so if we go back, then when, okay, so when that switch open, so, and this is what you have to do. All you have to do in this case is just write down what's going to be the condition. So this current went down, and then we got to write down here by how much, right? So that one went down to 6.35 amps. Ammeter number 2 is now 0. Okay, ammeter number 3 still remains the same, so no change. So all the other ones were not changed at all. Any questions about that? You okay? You're too silent. Sometimes you scare me when you are too quiet.
No, we're good.
You're good. Okay, so now what we are going to do is that I am going to close switch number 1 again, but now I'm going to open switch number 2 and see what happens. So from the last condition, when I close, excuse me, switch 1 and I open switch 2, then what is going to happen? Well, actually, this current here is going to go to 8.95. So it's going to go up. And then this one is going to go up as well from the last condition because it went from 0, it went up to 5.2. And then we are going to have that on A3. We didn't have any effects. It wasn't affected. However, A4, as I said before, it is the sum of resistor 3 and resistor 4. And because we open the branch L4 through L4, we lost that current. So if we lost that current, we lost our 2.6 amps that was flowing through that branch. When that happens, then we get 1.25 amps here. And indeed, from the 3.85, it dropped to 1.25. So yes, it went down. And then this one here goes to 0. And of course, if this was a light bulb, the light bulb would be off. Okay. So then what we do is that we just open both switches, both switch 1 and switch 2. And when that happens, because we are losing branch number, this branch here is being lost. And also we lost this other branch. Now the only resistors that are accounting for the total current of the circuit will be our R2 and R3. And everything is going to be dropping down to 3.75 amps. Okay, so from the last position, our current went down. So ammeter 2 is going to have 0 because you have an open switch. And then again, you can see that ammeter 3 remains unchanged. Okay, and in this case, from the last position, ammeter number 4 remains unchanged. And the last one then is just 0. Now, the last question would be, what's going to happen when R2 opens up? Would you like me to explain that part, or you want to give it a try first and try to do the simulation and come up with your own answer? What would you like to do going forward? Do you want me to explain that part, or do you want to take the chance and just check?
I would probably prefer you to explain it.
Okay, perfect. So now what I'm going to do is that we are going to have like both switches closed. So I'm going to be switching back to the simulation. So everything which, so I'm just going to show you my simulation, but everything that I have on the screen, on this screen so far, is going to disappear. But because I'm recording the video, you'll be able to see it. And also you have the answer key. Okay, so now, perfect. So what I'm going to do in this case, if both switches are closed, what was the resistor that opened up? It was this one?
Yeah, I think so.
Yeah, perfect. So what I'm going to do anyways, is that in order to be able to do it, to do the simulation this way, I'm just gonna increase the resistance like dramatically, just to simulate that it is open. So if the resistance was increased dramatically to 1 mega ohm, you can see that I'm just gonna be simulating that that is an open switch, but what's happening to the yellow dots? You can see that they all pretty much stop, right? So all these yellow dots that represent the current are showing that we don't have a flow. Yes, through the ammeter, because I am using 1 mega ohm, it's telling me that I have 130 microamps. But in this case, it just means that we pretty much lost that load. If this was to be like a resistive load for heating, we just lost that heater. You're not going to be getting any heat from 130 microamps. If we go back to its normal condition, let's check something here. Okay. Oh, sorry. I had the wrong slider. Okay, sliders here. How many ohms was that one? Remember? How many ohms was that resistor?
25 ohms.
It was 25 ohms. Okay, perfect. Thank you. Just put it back, 25 ohms. I just want the slider on this one. And that other resistor, how many ones was this one, or two?
52.
Pardon?
52.
82. Okay, perfect. Thank you.
52.
Oh,
52.
52. 52. Thank you. Okay, perfect. So just to finish this, when we have like our 52 ohms, yes, indeed, we are going to have our 2.5 amps. But if I simulate that we have an open resistor, then we are going to have like, we are not going to have any flow. So what's going to happen is that we are going to lose our current flow through that ammeter, and it's just going to be reading 0. And because we open one of the branches, now only 3 branches are accounting for the total current flow that we have through A1. Any questions about that? Okay, guys, so what I'm going to be doing going forward is that, okay, so it's completely up to you, but we are going to be having a quiz Tuesday. And because we are having a quiz Tuesday, the quiz is going to be based specifically on series and parallel circuits only. So all the other information that you studied before, you know, about like scientific notation, yeah, you should know your scientific notation and all this stuff, but you are not going to be tested on scientific notation. You are going to be tested only on series and parallel circuits and nothing else, okay?
So that's on the 24th then?
Pardon me?
That's on the 24th?
That's going to happen like on the, let me check once more. So is it the 24th that is Tuesday? Yeah, on the 24th.
No, that's Thursday, I think, isn't it?
Oh, no, the 24th is Tuesday.
Oh, sorry, I'm looking at the wrong.
No, yeah, the 24th is Tuesday. Yes, and it's going to be on circuits only. So please make sure that on their quizzes that you complete both the series quiz and also the parallel quiz. So you have 2 of them. One of them say that is available like pretty much today, which is the 18th. So just make sure you complete those quizzes because they are going to give you a good idea, you know, on how you are going to be tested. And yes, you are going to have like coupled circuits that you have to fill out. And when you fill in the answers, I don't want to see, like you can if you want, and I don't want to mark it wrong, but just try to write down your digits, okay, just the figures without any notations.
So we have another test on Tuesday then?
Yes, yes. Like,
okay.
I just want to remind you, like, if you ever have any questions on when is it that I'm supposed to have a test, when you go into the content, there's something which is called the instructional plan right there. So which you click on it, you are going to be able to see what is it that you are going to be learning week by week. Okay, so everything is there. How much each test is worth, and what is it that you are supposed to be learning on each individual week. The only thing is that on the second test, it says combination circuits, but combination circuits is not going to be part of your test. That's going to be reserved for the 6th week, week number 6. Any questions?
No, just get our series and parallel stuff all caught up, and that's all we have to do really until our next class.
Yes, sir.
All right.
And then after the test, okay, so it's completely up to you if you want me to open up this information, which is about combination circuits. But I don't want you to get confused. I don't want to take this chance of you getting confused with combination circuits and thinking that that's going to be part of your next test.
Do we need to do combination circuits by next Wednesday, though?
No, sir. So
just the parallel stuff?
Yeah, just concentrate on series and parallel. I prefer if you are feeling very confident on those 2 topics before we move on into combination circuits.
I did have one question about sort of like the parallel circuits in the
Sure.
handouts. I don't know if it will be covered next week then. It's about the multiple voltage sources in a parallel circuit. I don't know.
Okay, so can you tell me which question it is, please?
It's circuit 17 for parallel practice sheet.
Okay, let me check that. So which practice sheet it is? Number 1, 2?
I think it's number 3.
Okay. And in this instance, you say that you
No,
have...
okay, no, sorry. Then it's number 2. Then it's the one
Okay,
before that one.
Oh, no worries. So it's number 2. Okay, so that one, right?
Yep, that's the one.
Perfect. So in this instance, can you see that it says that, okay, you have a negative terminal, you have negative, and then the positive is connected to the negative. Remember what we were talking about, what we were saying about additive polarity?
Yeah, in the series, you'd add them together. That's the same thing then for...
Yeah, perfect. So this conductor here is going to be your neutral conductor. And this one in here is going to be 120 between this point and this point. And then the other one is like having line 1, and this is line 2, and this is your neutral. 120 plus 120 is your 240. So in this case, this resistor and this resistor are connected, let's say, to line 1 neutral, while the 20 ohm resistor is connected to line 2 to neutral.
Yeah.
Make sense now?
So then I would just use the 120 values for calculating at A and B and stuff?
Yep, perfect. That is absolutely right, because this is just to simulate the same exact condition that you have in a residential panel, where you have line 1 and line 2 and a neutral, and you all have your panel is supposed to be balanced, and everything is connected between line 1 and 2, which is 240 volts.
Yeah, so nothing in that display would use the 240 in the calculation though, right? Everything just uses
not
the
at all.
120 value.
Because everything is connected back to the neutral.
But to the neutral, yeah.
How would it look if it was 240? And we had to figure it out.
Okay, yeah, that's a very fair question. Like if I wanted this, if I had intended this to be 240, I just cut the neutral. And then now everything is connected as a combination circuit.
Okay, yeah, that kind of makes sense.
Yeah. So maybe in code, you have something that is called the broken neutral. So you can see the effect of a broken neutral in a circuit. And that way you can analyze why is it that is so necessary to have your bonding to have your grounding and bonding like in every single outlet. But well, guys, without further ado, like if you don't have any further questions, thanks for your questions today.
I just have one question about the last test.
Yeah, sure. Tell me. Oh, yeah. You told me, but I'm gonna stop live recording now, and then we can go over that question. Or do you want that to be part of the recording?
Yeah, it doesn't matter. It's just that one with the horsepower rating. I noticed it wasn't corrected yet.
It wasn't corrected